All right. That remains a hard act to follow. 30 years of interaction-free measurement already is a hard act to follow. And I also remember when that paper came out, and I remember when the work was out before the paper was out. Lucian already mentioned how one of the striking things is that this was a demonstration that you could still do something that was deep and interesting without being complicated. I'd go beyond that. What stuck in my mind as a grad student at the time is that people hearing this work at a conference had one of two completely disparate reactions. Half the audience was dismissive, saying, this is trivial, this is just interference, everyone knows this. And the other half was saying, my God, that's impossible, that's so deep. And it was the first time I'd experienced that. And I've seen it numerous times since then. I think everyone who works in foundations has experienced that. But to me, that's what we should always be striving for. That's the sign of an exciting result. When some people think it's trivial and other people think it's impossible, you know you've hit something important that you have a chance of learning from. Then I remember Paul went off and started working on experimental IFM, and I was very jealous of the opportunity to work on one of the most exciting things going on in quantum mechanics at the time. A little over a decade later, we got to do some related work with my students, Kevin Resch and Jeff Lundin, working on doing weak measurements on Hardy's paradox. But the talk I'm going to give now, although it's somehow inspired by all of the great conversations and discussions that I've been fortunate enough to have with Lev and Avi and Yakir over these past 3 decades, it's not on an experiment that was driven by IFM. I tried, nonetheless, to find a way of changing the title. Changing the title to absorption-free excitation, so that you may see a parallel between interaction-free measurement and what I'm going to be describing. But I'd say, if anything, the real parallel here is that lots of you are going to tell me at the end that the answer was obvious, and I hope a few of you tell me that it's impossible, so that at least we'll still have that discussion. Before I get there, I do want to say many of you are already aware of the John Stuart Bell Prize for fundamental quantum mechanics and its applications that's run out of the Center for Quantum Information and Quantum Control at Toronto. This is the call for the next nominations. You've got until August 30th to send a nomination if you think of someone whose work over the past 6 years merits this honor. Sandy Popescu is the past winner of this prize. And I want to give credit to the people in my group who really did this work. We work on a number of different things: cold atoms, entangled photons, non-entangled photons. But the work I'll tell you about today is in our atomic physics laboratory, and it was really led by Josiah Sinclair, building on some earlier work by Amir Feyzpour and Martin Halaji. This work was then picked up experimentally with Daniela Angulo-Murcio, Kyle Thompson, and more recently, Vida Nixon and Andy Chow. Grace Lee helped a lot on the theory, and the theory that I'll tell you about now was done in collaboration with Howard Wiseman as well. I'll talk more about their collaborations as we go on. So let me just give you the roadmap. What I'm going to do is pose a question. The question is very simple, and as always, I think that's where there's insight. When you look at something that you think we all understood 100 years ago and realize, wait a second, I'm still not sure how to think about it, that's where we make exciting progress. What are photons doing while they're going through a gas or a piece of glass, going through some dielectric? We should be able to understand that simple question. And I'm going to argue there's stuff about it that we haven't, or at least most of us haven't, spoken about carefully enough. And I'll provide a simple intuition, and I'll explain why there's a problem with it. And then I'll give you something rigorous that doesn't completely answer the story before describing an experimental result that honestly was a complete surprise to us. And working in foundations of quantum mechanics, I think, unless you make a mistake or unless you're John Clauser, you've finished by finding what you expected in the experiment. Quantum mechanics is right. And I'm often a little bit jealous, for the second time in this introduction, of my condensed matter colleagues who just study stuff so complicated they have no idea what they're going to see. Whatever they see is new and unexpected. It's, a number, a phase diagram, or whatever. And we keep confirming what we thought we were going to see. This is the first or second time in my experimental career that we did an experiment. We're like, shit, that's not what I thought we were going to find. And it took us a year or two to think about it and try to understand it theoretically. So to me, that's an exciting story. I'll also say this was one of the experiments in my group that wasn't really driven by foundations interests. This is when we tried to temporarily branch out and do something practical, figure out how to really make a useful 2-photon switch, a quantum logic gate, or at least take some steps in that direction. And here are a series of papers that were leading up towards this work. But one day, Josiah, who was leading the experimental effort at that time, came into my office and basically said, wait a second, I thought of something. Am I right? Because this makes it seem like it just won't work at all. And we got so derailed by how much more interesting it was when it didn't work that that's what we ended up doing for the next few years. We're still working on it. So here's the question. While a photon traverses a dielectric, and I'll use a gas of atoms as my example, where does it spend its time? What is the photon doing as it moves through that gas? That's all I want to know. And you sometimes hear what I always thought of as a hand-waving answer. This was, the answer people gave me my first year in grad school that, well, energy conservation, you can violate it for a little while. So even if the photon is way off of resonance, the atoms can get excited for H over that energy deficit, as long as it's a short enough time that they don't realize that they're violating conservation of energy. And of course, that language is flawed. We all know that. But still, there is this basic idea that as light propagates through a medium, there are some virtual excitations, and there's some time that the energy is spending as excitations rather than as propagating photons. And you can attribute some of the delay, perhaps, to that excitation time. And it's not completely crazy. If you look at the form of the index of refraction around a resonance, or more specifically, n-1, it turns out it does fall off as 1 over that energy deficit. When you're far from the resonance, this really does fall off as 1 over delta E, basically. And of course, on resonance, that picture is sort of silly. I don't need an uncertainty principle argument. If I'm on resonance, the atom can actually absorb the photon. So what do you expect to happen to the delay time on resonance? Sort of a different question. Maybe this whole picture breaks down, or what I would have thought is maybe the delay just saturates at the lifetime of the atom, the spontaneous emission lifetime, because that's how long the photon spends perhaps in the atom. Well, it's even worse than that. Those of you who know your wave propagation, electromagnetism, Sommerfeld and Briand, know that this is just the index of refraction. It describes the phase velocity of light. If you actually work out the group velocity, there's an extra derivative in there that becomes really important close to resonance. And the group delay, the extra time spent going through this medium, sure, it looks like 1 over the energy detuning far from resonance, but then it does this crazy wild stuff on resonance. It even goes negative, superluminal, and there's been lots of controversy about that, but I'll just move on. In any case, life is more complicated on resonance. So let's move away from the hand waving, and I'll tell you something rigorous that we realized we could say. It's actually something that we sort of thought was intuitively obvious, but we weren't sure it was mathematically true. And eventually we found that it really is mathematically exactly true. I don't know how many people are really aware of it. I'll skip some of the steps, but basically it amounts to saying, if I've got 1 photon in a laser beam coming into a sample of atoms, ask yourself what happens to each atom that sees that photon. What's its probability of excitation? And semi-classically, we know how to solve that. It's proportional to the intensity, at least in the low intensity regime. And really what it comes down to is the number of photons per absorption cross-section per atomic lifetime. It's pretty straightforward. So strictly speaking, that's the time integral of the excitation probability, which is my working definition of how long did the particle spend in the excited state, right? That's not a fixed number. It didn't spend a fixed amount of time in the excited state, but the reasonable way to define such a question is to integrate the probability over all time.
Ephraim?
Yeah.
Quick question. This intermediate state with this virtual absorption, is it a classically forbidden state?
No, classically allowed state.
It's classically allowed.
Classically allowed state. What I was imagining before is going through a piece of glass. So it's a classically allowed state, but you're far off resonance. So you don't excite it. You don't really excite it, so to speak. But in this talk, I'm actually going to go to the resonant case. So just on the resonant transition of a 2-level atom. And that's where this calculation makes sense. I should have said this calculation is for the resonant case. Now, of course, there are lots of atoms in here. And if you define the optical depth, basically the logarithm of the transmission minus the logarithm of the transmission of the cloud, it just has to do with the column density of the atoms, in particular, the number of atoms per cross-section that get in your way tell you how much you absorb. So if you put that all back together, and again, I'm skipping the steps. I'll happily go through this slowly with anyone who cares later, but I don't think that's the important part of the message. The total excitation time integrated over all the atoms just turns out to be that optical depth times the spontaneous lifetime of the atoms. Now, why is that interesting? Let's focus on the limit where the optical depth is small. We don't need to, but the calculation is easier. The transmission, by definition, is e to the minus OD, which means the absorption is 1 minus that. In the limit of a thin medium, then the OD is just exactly the absorption probability. So what we're really saying is the time all the atoms spend integrated in the excited state is just the absorption probability times the spontaneous lifetime. And that's what Josiah and I expected early on, because the easy way to understand that statement would be to say, well, look, I'm on resonance. I've got a thin sample. Some photons just fly through the sample and they get lucky and they reach my detector. Other photons get absorbed by atoms. And if it's one photon at a time, there's no stimulated emission or anything. It gets absorbed by an atom. That atom's going to spontaneously emit. Odds are overwhelming that it won't reach my detector. So I lose all of those photons. How long does it take to lose them? Well, they excited an atom, and the atom takes a spontaneous lifetime on average to spontaneously emit. So the total amount of time that the atoms have spent in the excited state is just the number of photons they scattered times their own lifetime. And that means that the transmitted photons are the ones that never excited any atoms. And that was the surprise. We realized that although you're shining resonant light on the sample, if you focus just on the photons that get all the way through, those are the photons that missed all the atoms. They'll have no effect on anything. And that was the fascinating thing that we wanted to test. So here's what it looks like a little more schematically. A photon comes in. For now, let's imagine one photon at a time, even though that's not quite how we did the experiment. Some are transmitted and will reach a detector. Others will get scattered out somewhere. And along the way, if they spend time in an atom, that reduces the number of ground state atoms, increases the number of excited state atoms, and that changes the index of refraction, which means we can probe that with a separate beam indicated there in blue as the probe. And this is an example of a nonlinear optical effect. It's well known, it's a kind of Kerr effect. Basically, the idea is here's my Lorentz dispersion relation, the index of refraction versus frequency. But if I remove some atoms from the ground state using this pump photon, then I'll lower the amplitude of this whole thing. And I'll see a different index of refraction for my probe. So I'll see a phase shift on the probe that depends on whether or not that pump photon created an excitation. And that was the question we were asking. Does that occur only for photons that are truly absorbed? If we look only at transmitted photons, will we see that there is no nonlinearity, that the probe photons don't care about that transmitted pump? So we turn this on the side. We send a probe beam through the sample. We have a way of measuring a phase shift. And we then also, and we argue that phase shift is basically a measure of the time integral of the excitation probability for the atoms. But we then add a single photon counter down here. And we check whether the photon got transmitted or not. And we condition or post-select on that. We look at the cases where the photon was transmitted. And I want to ask, on those cases, what did the probe see? So in other words, not how long does the average atom spend in the excited state for the average incident photon, how long does it spend in the excited state when the photon reaches the far side? Well, let me back up. To give you an aside to tell you how we really did the experiment is based on some of the previous work we've been doing before Josiah's idea. We were using post-selection to study what single photons would do, because although we had built ourselves a resonant single photon source, it could put out about 100 photons a second. And we were trying to measure things on the order of 10 to the minus 5, which would take something on the order of 10 to the 10 events. And we couldn't keep the system stable for more than about 24 hours at a time. We just realized the rates weren't sufficient in those days. We wanted to use a classical source, but we wanted to know what single photons were doing. So here was the first experiment where with Greg Machovsky and Amir Feyzpour, we were trying to see nonlinear optical effects at the single photon level. And we started with classical pulses. Here were pulses that on average had 5 photons, and we were able to measure a phase shift of about 50 microradians. We went down to 2 photons, and we were about to go down to 1 photon, not a single photon pulse, just a coherent state with 1 photon. When we said, shit, it's a coherent state, we could go down to half a photon. Why stop at 1? We could send in pulses with half a photon and then check, was there a photon there or not? And we'd be able to see when this goes click, what do we find? When it doesn't go click, what do we find? And sure enough, when we didn't go click, we really saw there was no phase shift. Whenever we saw a click, we saw there was a phase shift. And we said, hey, we're really seeing the effect of a post-selected single photon. So we're measuring something truly quantum. I don't need to calibrate as I did here and say, we're pretty confident they're on average 5 photons. We could really see when the detector clicks, you get an extra phase shift. But then we went through it more carefully and we realized, you know, you don't even need to go to half a photon. You can do this for any amplitude of coherent state. If you look at what happens when there's no click and you look at what happens when there's a click, there's always a difference of 1 quantum. There's the extra phase shift you'd expect from 1 more phase shift. From 1 more photon. And we worked that out. First, I just worked it out using Bayes' rule because it was kind of obvious to me that this was a classical treatment. My students said, why in the world are you confident you can use a classical treatment? They spent a week doing the quantum field theory and they showed that Bayes' rule was correct. And then a while later, we understood a more physical argument. And I really liked the physical argument, so I put it up here. We've got a coherent state coming into an inefficient detector. And as people in quantum optics know, you can model an inefficient detector by imagining that you had a perfect detector, but there was a beam splitter here that lost some fraction, only transmitted a fraction eta. The thing is, a coherent state reaching a beam splitter splits into 2 coherent states, one with amplitude root eta times the original alpha, one with root minus eta. Doesn't matter so much that they're coherent states. What matters is that this is a product state. What does it mean that it's a product state? It means that by putting this detector here, sure, I learn whether there are 0 or 1 photons in this arm, but I get no information about the other arm. It's left in that coherent state. So we can conclude how many photons there really were. Over here, there were alpha squared times 1 minus eta photons. And over here, there used to be alpha squared times eta, but I resolved that into either 0 or 1, depending on whether the detector fires or not. So the difference is strictly 1, based on that very simple argument. And to me, that's an argument about how many photons there really are. Philosophically, more careful people yell at me when I say things like that. But from a weak measurement kind of, two-state formalism kind of perspective, you realize that you're perfectly justified in propagating this backwards and saying, I do know the total photon number, or average total photon number, from the post-selection as well as from the pre-selection. So that's what we were using in that experiment. And then what we started wondering is, if every time the detector clicks, I say that means there really was 1 more photon than when it didn't click. By looking at that difference, am I actually learning about the history of that one particular photon, in the background of all the other guys in my coherent state? In particular, could I put this into some more interesting interferometer? So here's a 2-path interferometer for that pumped or signal photon. And you can think of that as being a 2-state system like anything else. This turns out to be equivalent to the original kind of measurement of the spin of a spin 1/2 particle yield a value of 100. Measuring the occupation number of one of these 2 paths when I send in a single photon, I can have a weak value of 100 or minus 99 or whatever else you like. So with Mateen Halaji, we did this experiment and we did the calculation. We showed that indeed, if you look at that difference, you really do get that single photon weak value on top of a bunch of other background. More recently, just last week, with Howard Wiseman, we published a more careful proof that generalizes that stuff that we'd shown with Mateen and really shows that for a broad range of situations, if you take weak values of photon numbers in networks populated by coherent states, post-select on single photons, that difference is guaranteed to give you the correct single photon weak value. So you really are learning about the history of this one extra photon by doing that. So that's what we chose to do with Josiah. But now for absorptive nonlinearities, this case where we were saying it should be 0. So we took a cloud of ultra cold atoms, sent a probe beam through the atoms, measured their phase, sent some signal pulses with very few photons the other way, looked at a photon detector, compared when it clicked, when it didn't click, what happened over here. And we said, well, that's going to tell us how much phase shift a single transmitted photon contributes. And it was a tour de force experiment. I'm not tooting my own horn, but that of my students. They spent something like 600 hours taking data, and it only took them about 1,000 hours to spend those 600 hours taking data. In other words, they didn't sleep very much during those few months, taking billions of pulses. This is just a sense of what the classical phase shift looks like. These aren't single photon effects. These are pulses with about 34 photons on average. And we get phase shifts that you see are on the order of a few hundred microradian. And yeah, we can measure them reasonably well, but you see there's a fair amount of background there. Once you do the subtraction to look for the single photon effect, it's noisy as hell, but fortunately we know what it's supposed to look like, so we can fit to background plus the expected shape and pretty clearly see something extra does happen in that region. So put that together and get the effect of one photon. So it's a single 600-hour data point. And the important thing is it's not 0. It's just not even close to 0. And we came up with a bunch of different models that are drawn here. I won't go into them because they're not right. But we tried to understand, how can this be? Where did we go wrong when we said the transmitted photon was the one that didn't get absorbed? Or put another way, if the transmitted photon, if it did get absorbed, why did it keep going to the detector instead of being spontaneously emitted? There were other photons around, but we were well below saturation. There's no stimulated emission going on. I can make this argument a little more hard-nosed by going back to our earlier intuition from that sum rule. Remember, before I talked about post-selecting, when I just said we've got some number of photons going in, I said, oh, look, the excitation time turns out to just be equal to the probability of loss times the spontaneous lifetime. And I thought that made sense because the time a lost photon spent in the excited state should be the spontaneous lifetime. I'll get to you in a second, Paul. If that's not true, if as we measured, the transmission time is also some positive number, there's positive contribution here, the time spent by lost photons in the excited state must be less than the spontaneous lifetime. So the corollary question is, why, when a photon gets absorbed, the only photon gets absorbed, does it get re-emitted on average faster than the spontaneous lifetime? Paul?
Yeah, sorry, I'm feeling like I need to get this message. So how do you know that you're not absorbing the photon and then re-emitting it in the same direction? There's an enhanced form of scattering, but it isn't like the optical theorem, right? All the phase of that up going in the forward direction.
We don't know that. We just thought it without thinking very carefully. You're exactly right. So this is what we begin to think now. That it does get coherently reabsorbed in the forward direction. And one way of thinking about this is to recognize we did this experiment with very short pulses, because if you were looking at that data, there was a lot of slow variation. And the only way we could separate the signal from the noise was to have a short pulse in time before anything else changed. So these pulses were shorter than the lifetime of the atoms. They had a larger bandwidth than the atomic line width. And again, as the optics people know, when a narrow pulse propagates through a dense medium, it picks up a phase shift. It actually starts evolving towards what you might call a zero pi soliton, a pulse that still has energy, but whose envelope integrates to 0. So the electric field envelope will start to look like this. And if you think about an electric field that looks like that, you look at what happens on the Bloch sphere, you rotate the atoms up, you rotate them back down, and even with a single photon, sort of linear propagation, you're right, you can coherently drive atoms back towards the ground state, which means that although they spent some time in E, the energy comes back out in the forward mode. It's not undirected spontaneous emission. It's also not stimulated emission. So we blamed this for our effect, and we said this also explains the other thing. It explains why the lost photon spent less time than a spontaneous lifetime in the excited state, because there's an extra mechanism pulling energy out of the excited state. We've shortened the lifetime of the excited state also by this coherent emission. And that all kind of hangs together. And we realize it's unfortunate that we had short pulses at a high OD. It's a nice model, but on the other hand, it's a semi-classical model. It can't actually give me a rigorous prediction for what we're measuring, because we're measuring the interaction between two different beams. And in the end, we're looking at entanglement. We're generating entanglement between that pump photon that's either transmitted or not, and the phase shift on the probe. So although it's nice to have heuristic semi-classical arguments, we wanted a full quantum calculation as well of what goes on. So here's how we're going to do that. We're going to use basically the weak value formalism. We're going to define an observable that's just an integral of the excited state density over the whole sample. And that'll basically be the thing that we're trying to measure with this instantaneous phase shift. And we're going to sandwich that between an initial pulse coming in from one side and a final state that means the photon actually getting out the other side, not having been absorbed. That was sort of obvious early on, except I didn't know how to do it. What complicates this situation is that this is an open system. So it's not just Hamiltonian evolution. We're actually irreversibly losing photons along the way. And I tried a few times, couldn't figure out how to deal with it. And it was really Howard Wiseman's insight how to properly deal with that, deal with the non-unitary evolution, correctly renormalize the state, and get all the math right, or the maths right, as you would say. Here's a video of what's going on. This is a pulse going through. That's a zoom in on the atomic region. And what you see again is the pulse picks up a phase shift after it propagates through. You could get that from the classical Maxwell-Bloch equations. But the time reverse pulse, you see it here also exciting some atoms, does not come back and give you anything that looks like the incident pulse, right? Because we're time reversing this system that has loss in it. That was kind of the complication. But it's mathematically well founded. We define the thing we're measuring, this thing I'm calling a transmission time, by the real part of the time integral of the weak value of this object. Again, just the real part of the weak value of the projector onto the excited state. And lo and behold, we find if you go to thinner and thinner media, lower and lower OD, where you don't have time to create that phase flip that does the coherent emission, yeah, the time does begin to drop towards zero as we expected. Better yet, we can now go to longer pulses that are narrow band, where we thought the story would be simple and you don't get any of this coherent emission. And we can do that too, and we get these beautiful curves, except they don't just go to zero. They go wildly negative first, and then they go to zero. And first I yelled at my students and I said there was a sign error in their code. And then one of them was clever enough to take the limit and, prove analytically that Howard's formula was really going to give you this negative slope at the origin. So I yelled at Howard for a while that he forgot a minus sign, but Howard doesn't forget minus signs. And no, this is correct. And once more, we eventually supplanted the calculations with some intuition. And here's a diagram that should be familiar by now. We realized we actually got a time that approached minus the OD times the spontaneous emission time, instead of plus the OD times the spontaneous emission time. It sort of looked like a, probability, a weak value projector of -1, which are familiar, right? That's what you see in things like the 3-box problem. When you have an interferometer and you flip the phase of one of the paths, you can end up with that minus sign remaining for the weak values. I thought that was kind of interesting. Can we think of what's going on between the light and the atoms as a kind of interferometer? Well, everything's an interferometer, so the answer is yes. In particular, there's coherent interaction between the electromagnetic field and the atomic excitation. So you can think of discretizing that interaction as a whole bunch of beam splitters, where at each interval of time, it's possible for a photon in a ground state to turn into an excited state, no photon, possible for it to turn back. So the simplest little unit cell of that kind of a cascade that would be interesting is to start with one photon, but atoms in the ground state. And so, all right, there was some amplitude to end up in the excited state, some amplitude to end up in the ground state. And then we interact again. So the excited state could go back to the ground state, or we can end up in the excited state. And what we want to know about is when I see this 1G, I see a transmitted photon. Was I in the excited state beforehand? That's what we're trying to measure. How much time did I spend in this path before coming out here? And the thing is, even though we're interested in this regime where almost everything is transmitted, if we're on resonance, in some sense, that's still the dark port of the interferometer. Because being on resonance means you have constructive interference into the excited state. So projecting onto the excited state means projecting with a plus phase between these two paths, same thing that we excited coming in. And looking at the transmitted port is actually with a minus phase. Now, if it's a short time or a thin medium, this omega dt is small. I'm mostly in the ground state everywhere, and I'm mostly transmitted. But even though I'm mostly transmitted, it's still the port with destructive interference. It's still the port with that minus sign. And when you plug that minus sign into the weak value for the projector onto this B path, the one where I'm in the excited state, it's exactly like in the 3-box interferometer or any of the others. The minus sign does not remain when I calculate the expectation value, but it is up here when I calculate that matrix element from I to F, and therefore it's there in the weak value. So the weak value of this observable probability of being in the excited state turns out to be exactly minus the expectation value. The expectation value was scattering probability times tau spontaneous, and here we get minus that. Blah, 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 I already said that. One thing to note is, to me, this is a really interesting case in that we're looking at an anomalous weak value, right here, a projector that has a negative weak value, but it persists even into the limit where the post-selection probability approaches 100%. It gets smaller and smaller, so the expectation value is always well behaved, but it remains negative all the way down there. Well, thinking about it more, thinking about that slope of minus the OD, again, those of us who thought about these kind of resonant effects would recognize that and say, you know, I showed you that negative group delay before, and just by dimensional analysis, you might have realized the value of that negative group delay on resonance is exactly minus the OD times the spontaneous lifetime. So in fact, this prediction we were getting for the narrow band pulses was just the group delay, which comes back to that intuition I started with, right? That the extra time it takes to go through a medium has to do with how much time you spend in the excited state. Well, on resonance, you don't spend extra time, you spend negative time. This argument says, well, that's okay. That negative time is how much time you spent in the excited state. And in fact, we were then able to prove analytically that Howard's expression, that complicated weak value integral, really is mathematically equal to the group delay. And if you do it for a short pulse, it's equal to the appropriately spectrally weighted group delay that basically says how much time did the center of mass of the pulse spend before getting out of the medium. Now, again, there's that sum rule problem. I said that if the transmission time was positive, then somehow the lost time was going to have to be smaller than the spontaneous lifetime. But then wait a second, if the transmission time is negative, that means the lost time is going to have to be greater than the spontaneous lifetime. What's going on there? It turns out this was already known. The time it takes something to scatter off of a thin resonant medium is not the spontaneous lifetime. It's something people call the Wigner time. Antoine Paet's group actually measured this experimentally a few years ago. And it goes to twice the spontaneous lifetime. I'd seen this formula decades ago. I looked at it and I said, well, of course it's on the order of 1 over gamma. What else could it be? And I never bothered to look at the 2. But the 2 is huge because the intuitions really do say the fundamental timescale here is 1 over gamma, not 2 over gamma. The reason this is 2 over gamma is precisely because the other thing is negative, and it's just negative enough to compensate for that. Now, if you go to a thick medium, it gets a little more complicated because first light propagates through some of the medium up to about 1 optical depth, and then it gets scattered with the 2 gamma. But the group delay was negative, so you add the negative propagation time, the 2 gamma. This is what you get for different pulse widths. It begins at 2 for something narrow band, a little below 2 for something broader band. But then as the optical depth tends to infinity, it saturates at exactly 1 spontaneous lifetime. That is the limiting case. And, well, never mind that. This one's a little bit busy, but if you then combine our scattered times for the scattered photons in solid lines and the times for the transmitted photons in dashed lines for a range of different bandwidths, what you see is for the really narrow band, infinitely long pulses, you get this negative transmission time, minus OD times the lifetime. And the lost time is just growing linearly over here. On the other hand, in the short pulse case, the broadband case, you actually begin close to one lifetime for the scattered photons, you dip down, and then you slowly climb back to one. So what goes on with the transmitted photons is they start getting a negative time, and then eventually, as in our experiment, because you're dominated by stuff that's off resonance, you end up with this positive time instead. Anyway, still a lot of complicated behavior in a problem that we thought we understood. And I hope that what it can teach us is that this group delay that we usually dismiss as, a real effect, a real interference effect, but not the amount of time something really spent there, is in some sense the amount of time it really spent there. And I think there's a fascinating connection to a recent experiment from Bob Boyd's group on what's known as the transverse Fizeau-Drag effect, where if you have a dielectric that's moving, as in the original Fizeau experiments, but not moving along the propagation direction of the light, but moving transverse to it. So you send in light perpendicular to this moving fluid or whatever, the light comes out displaced a bit to one side. And it turns out in the normal case, except for a small correction, that displacement is just equal to the extra group delay, the time you might have said the light spent in the medium, multiplied by the velocity of the medium. Makes perfect sense. Well, it turns out you do this in a region of anomalous dispersion, where the group delay is negative, and you get an anomalous Fizeau-Drag. The light actually comes out in the opposite direction. And if you like this simple argument that it spent a certain amount of time in the medium and the medium was moving, it still works as long as you say the amount of time it spent in the medium was that negative number, and it really was equal to the group delay. So I think there are more and more effects that we can at least learn to think about better by thinking about these post-selected cases, thinking where the photon really was. The morals then are that that picture remains coherent, no pun intended, even when the time is negative. The negative time is necessary to compensate for the factor of 2 in the Wigner time. And I'll mention, a lot of people might say, well, we already know that a nonlinearity requires things to be in the same place. I forget who had this great quote about why they want to use nanostructures for quantum optical nonlinearities. They said, if you put 2 people in an elevator for long enough, even if they're physicists, eventually they'll talk to each other. The same is true for photons. So if you have a really, really long group delay, you expect a big nonlinearity. A really short one, you expect a small one. The thing is, that argument is used in classical nonlinear optics when they're not doing any post-selection. People use that argument just to say the overall effect of the average incident photon is going to get bigger. That's not at all what we're saying. We're saying the group delay describes the effect of the transmitted photon. And in fact, that can even have the opposite sign of the effect of the average incident photon. So it's different to that traditional argument. And Daniela is now leading an experiment to confirm that negative time prediction. And we have nice preliminary data that I think are going to do that. So with that, I'll thank you for your attention and I'm open for questions.
The very interesting physics you discussed reminds me of 2 works which might be somehow related. One is a work we did a few years back, not in optics, but in condensed matter. Has having to do with an electron injected into a quantum dot, which is not at resonance. So the quantum dot is in a Coulomb blockade regime, and when the electron enters the dot, you obtain a state which is classically forbidden. The energy is classically forbidden. Okay. But then the electron, which is the equivalent of your photon, and the other electrons in the dot, which will be the equivalent of the atoms, are excited. But then the electron needs to decide whether it goes back or goes forward. Yeah. And one can define a weak measurement, which will measure the time of this excitation and phase shift.
All right.
due to this. So that's one work. And the second work, which is perhaps more remotely related, is the stuff that I discussed yesterday. I measure a spin. My detector is a spin, and my detector can click and then unclick, so that the detector can find during the measurement in a virtual state. So these are
Yeah, no, I was thinking that during your talk yesterday. Certainly it is an interesting connection. And, of course, and as Paul also said, and other people observed to me, we know these coherent effects exist. That's the standard second order effect. It's in all the textbooks. We somehow thought in our regime that wasn't going to be relevant. We dismissed it. The first work I wasn't aware of, so I look forward to asking you more about that and reading that. That sounds really closely related and very interesting. Thanks. Yeah.
Just this last thing with Bob's thing there. I'm very curious what you think about. Can we just observe this in the Earth's rotation? For example, if you were to send, could you use this to actually measure the rotation of the Earth by just sending light beam through versus having one with this dispersed behavior?
It seems to me, first of all, that it would be a higher order effect, but in the reference frame of the air, of course, this isn't occurring. So you're really just looking at the fact that you're doing electromagnetism in a non-inertial frame. If you go to the inertial frame, then I agree with you. In the inertial frame, you have to take account of this piezo drag effect. I think the longitudinal one would be much easier to measure. I don't see a good reason to use the transverse piezo rather than a longitudinal, because now you have to measure a transverse shift of the beam instead of a phase shift, microsym or something like that, right? But I haven't thought about it before. My initial reaction. Yeah.
So you mentioned this group delay comes out of this integral over the weak value. Is there a case that you've seen where the weak value is complex and not just plus or negative?
Sorry, we are using the real part as our definition here. And I don't believe that the imaginary part is vanishing identically. I think we're just discarding it. And I'm sure at some point we had some discussion about whether or not we could figure out what it meant, but I don't even remember the outcome. So that's something to follow up on. Yeah.
Is it true in this left-going drag thing, which I find quite mind-boggling? Is it true that that's always underneath this overall envelope, and you're just post-selecting one section, or really you send a beam in and the entire beam goes to the left?
No, the entire, the shift is usually smaller than the width of the beam, but no, it's true for the whole beam. And honestly, it's easy to derive classically that this has to just be the group velocity times the velocity of the medium. You do the same thing you do for the normal piezo effect. Transform into the moving frame. The problem is when you transform into the moving frame, this beam is no longer at normal incidence, and now it refracts. And there, more importantly, sorry, the right way to do it. There is an angle-dependent Doppler shift, is what I probably should have said. That's the easier way to see this. So this localized beam has many different k vectors, but each one sees the resonance at a slightly different position. So if you want to calculate where do I get interference, like the group delay calculation, you're taking a derivative of the transmission phase with respect to that angle. But that angle is giving you the Doppler shift. So that really is the derivative of the transmission phase with respect to the detuning. So mathematically equal to the group delay and the constants work out. So you shouldn't be surprised that this is negative when the group delay is negative. But the fact that there was this appealing interpretation that the energy spent some time in the atoms and the atoms were moving, multiply those two things by each other and you get the shift. That only works if you take seriously that still applies even when the time is a negative number.
I think we can develop better intuition for the patterns in all these cases when you have three projection operators, well, two are positive and one negative. That this button, there's a better way to develop intuition is to think about it not as one photon every length of time, but actually as three photons moving there. Two of them are normal one, and one has negative energy, and that picture will give you a better information what's going on.
You've told me this many times, and in your talk yesterday. I haven't thought yet about how to apply it to this case where I don't actually even have three boxes, but in some sense only two.
No, it doesn't matter. Even if you have, let's say,
I guess
this
there's one place where I'll have 1.1 photon,
No,
where else I'll have 0.1 negaphotons.
the three projection operators now are three different vectors in Hilbert space. And you can say that there's like if I have spin, for example, spin up, I can say for spin up there are two normal particles, for spin down there's one negative particle, they intermove together. But they still special sensation about it intuitively as being three particles there. So the normal and one the opposite. So you can develop mathematical intuition as I try to explain yesterday myself.
Thanks. The branch.
I'm Frank, but my apologies, maybe that's a very, very naive question. I will try to recall my atomic physics lectures. So, assuming that we have a dynamic experiment that we are about to go with a quadrupole foundation. So, I think let's say full of system is beautiful and very clear, very nice presentation, by the way. What's happening if I assume that I have some kind of action that current allows me to go with a quadrupole transition? Of course, the time may be different. I mean, the time
I don't see why you expect it to change anything fundamentally.
because the time of flight for the beam that provides the expectation is different.
So I have to use the appropriate lifetime, the appropriate cross section, the appropriate group delay. And I think those are the only quantities I need. I didn't make any dipole assumption otherwise.
I'm talking about the by itself. So if those beams they propagate with a velocity which is below the speed of light in vacuum, if they are false. Due to the transition in space.
I see. You're not talking about a quadrupole transition, but
But itself, like also the beam.
then I don't have a quick answer. My guess would be that this kind of treatment describes the additional delay due to the interaction. And you just have to add that to the free space delay. But that's intuition, and I'd be happy to learn more about what these quadrupole things are doing. Do you have an answer for
No. I was just wondering, if your ideas could be used to solve what Avi was raising in his ideas yesterday about actually having, you're basically having a non-local router, right? You're basically now you could think about these atoms instead of being localized, actually having some sort of non-local distribution. Anyway, this is thinking out loud, but I just wondered, as you were talking about your single photon switch, if that could actually be used to solve some of the things that Avi was proposing.
I don't immediately see how it's either non-local or a non-local router. What it does with the switch is certainly interesting, right? You know,
Well, it's not that your atoms are
The Shutter experiment was conducted in New okay? The Shutter experiment.
yeah.
Okamoto was Okamoto did his postdoc. So this is very low about the Shutter experiment.
Actually, he knew about it before I but we talked more about it. Yeah.
But you conducted single experiments close to each other?
We just did the 3-box version of not shutting. And
What particle was it?
I'm sorry.
Which particle was?
We talked about it, but we did, the closest thing we had to an interaction was using a kind of rail cross-like destructive interference. So we used a nonlinear crystal in Kevin's experiment to get 2 photons to optic convert to effectively annihilate. Whereas he used, really used an actual, quantum logic gate, quantum logic gate, which is better, which is really good. We didn't build it into the whole shutter setup, which I think they had a lot, or do the straw machines. We just did a weak machine.
Now I outside, it's like it's.
I didn't necessarily mean non-local, in that it was here and here, but it's this, when you're probing that with your laser beam, your atom can be in multiple locations within that laser beam. That's the coherent effect.
Right, and of course, it's a weak measurement. All we're doing is measuring the integral of the weak value local projectors.
Yeah. But one other question I had, I was interested in knowing that your spontaneous asymptotic approach in the large optical depth limit, that it approached 1. And I would have guessed that if you had started to have multiple scatterings, when you started to get high optical depths, and that would have increased your spontaneous.
So, first of all, it wasn't obvious to us to do the first one, other than calculating it. I don't think I can give you a clear argument why not do it. Secondly, we're not doing any multiple scattering, so this would be appropriate for high optical depth, but a narrow medium with high optical depth. What would happen in the multiple scattering case? Certainly not going to put it stable.
Okay, today. Okay, English from